All right, phase changes. Phase changes are this relationship between the states of matter, kinetic energy, and intermolecular forces. So think about the intermolecular forces that we've already talked about. So in a solid, the intermolecular forces are stronger. They're holding them in that rigid line of soldiers type mentality that we saw. And then as they get a little bit looser, if we can overcome those intermolecular forces a little bit, we can start to slide around each other. And that's allows a little bit more motion. And then the intermolecular forces are the weakest when we get the gas. And so what's going on is that the kinetic energy, as we go this way and we heat things up, remember, as we heat things up, they gain more kinetic energy. They'll be able to eventually overcome the forces holding together. So if I take ice and I heat it up, it's in that rigid formation, but as it moves more and more, faster and faster and faster, it manages to break loose of those intermolecular forces and be able to slide by each other. And then if I continue to heat it, eventually they break even those intermolecular forces and start flying around randomly. The same goes in the opposite direction. As I cool things off, they get to the point that the intermolecular forces begin to drop and cause it to solidify. All right, so the basics. So we got the 6 types of phase changes, and the first 4 are pretty simple. That water to ice we call freezing. Hey. Ice to water, we call that melting. No kidding. All right, gas to liquid. Water vapor to a liquid on the outside of your cup. We call that condensation, or on your shower mirror. All right, vaporization is the bigger term. Do not call this evaporation. Evaporation is a subtype. Evaporation is when you take something from a liquid to a gas without adding any extra heat to it. I leave a cup of water out, it evaporates over time. So when we put things on the stove and we're turning them into steam and boiling water, we don't call that evaporation. We call that vaporization. All right, these two over here, sublimation and deposition. You've actually seen both of these before. So the easiest one of sublimation is dry ice. It goes directly from a solid to a gas. And so it's said to sublimate. Okay? It's called dry ice because it never gets wet. It just goes from a solid to a gas directly. You will also see this, you'll see both of these in your freezer. That if you leave an ice cube in your freezer, over time the ice cube will get smaller. It's not melting in your freezer because it's below freezing in your freezer. It is simply turning into a gas slowly over time. Same thing if you get frost on something. Frost is an example of deposition. Same thing as frost on your grass. Frost is not frozen dew. Because if it was frozen dew, it wouldn't look like ice crystals, it would look like frozen water droplets. Same thing with snow. Snow is formed by deposition. The gas in the clouds, the water vapor, goes directly to a solid. If it went from a gas to a liquid to a solid, that would be sweet. Okay? Because that's what would happen here. That's where the freezing would happen and you get sleet. So snow is actually a form of deposition. And so you can kind of see, you do have experience with these, we don't talk about them as much. And so that's the basics of the changes of states of matter. Now, we need to look at what this looks like a little bit more chemically. So we got 2 different curves we need to look at. First one's called a heating curve, and it looks like this. So I add some heat, and my temperature goes up. I go from a solid, and then it levels off. Then I melt, and then I become a liquid. Then it levels off, and I vaporize, and then I become a gas. Okay. So a heating curve allows us to see what's going on. The key to this diagram is this. When you are undergoing a phase change, there is no temperature change. A pot of boiling water, no matter how high you crank that heat, will never boil hotter than when it started boiling. It won't happen. A glass of ice water, no matter how much ice you put in it, it's not going to get colder. Once it gets to ice water, it's not changing because that's where this is going on. This melting phase is happening. Temperature is going to remain constant. Now, that's assuming you're stirring. Like, the ice at the top may be colder than where it's liquid on the bottom, but assuming you're stirring and all that, this is going to be true. Because all that energy that's being put in is no longer moving, making the molecules move faster, so it's not changing the temperature. all the energy that you're putting in, all this heat you're adding, it's simply going into overcoming the intermolecular forces. And that's what's going on during a phase change. And that's why the temperature doesn't change. So you're overcoming those intermolecular forces, and it keeps the temperature the constant. And then once we get all the way to liquid, then we can ramp up the temperature again until we start boiling. Then once we get steam, we can take steam and we can heat it further past that. So that's a heating curve. Once again, main thing there is that temperature does not change during a phase change. That's critically important. All right, phase diagrams. These look a little bit weirder, and you got some things that you're just not familiar with here. First thing, that both pressure and temperature affect phase change. Now, the fact that pressure affects phase change, that seems strange to us because we generally live in a world that's at constant pressure, it's at atmospheric pressure. But if we look at this diagram and we see, let's look, for example, the difference between, this is water's phase diagram, the difference between liquid and a gas. So any point on this line is where boiling can occur. And so let's say this is normal atmospheric pressure. Well, what happens if I increase the pressure? I have to increase the temperature to get back to the line. This is how a pressure cooker works, where you boil water at normal temperature here. In a pressure cooker, because the pressure is higher, the boiling has to occur at a higher temperature. And that's why pressure cookers, like your Instant Pots, that's why they cook faster, because they're literally cooking at a higher temperature. And so it allows them to cook things more quickly because you change the pressure. The opposite is also true. You can also decrease the pressure to cross this line. It is possible if you have a strong enough vacuum pump to boil water at room temperature. That if you take water at room temperature here, you can either heat it this way to boil it, or you can drop the pressure. And that would also cause it to cross this line and move into a gas. I've never had one in my lab strong enough to boil water at room temperature. However, you can find YouTube videos showing that very process happening. All right, so there are other two things that are fairly important here. First, there is a solid-liquid transition that bends left for water that makes it unusual. Most things go this way. It means you can actually freeze water or you can melt ice, by increasing the pressure. But we also have some other things on here that are critically important. So, for example, this guy right here. This is called the triple point. And if you look at it, so if I said this is where boiling happens, this is where freezing happens, this is where sublimation and deposition happen, what's going on here? Well, as the name implies, all three states of matter are present at the same time. You get boiling ice water. That kind of messes with your head, doesn't it? So you get boiling ice water. Once again, there are videos out there. Veritasium, which is a YouTube channel that I really enjoy. They have a good one with showing nitrogen at a triple point. You get solid nitrogen, liquid nitrogen, and gaseous nitrogen all present at the same time. The easiest triple point to reach is carbon dioxide. And so that's the one you'll commonly see online in YouTube. And then we also have this point on the end called the critical point. So when you get past this, when you get beyond this temperature and beyond this pressure up into this area up here, you reach a point where, as it says, the distinction between liquid and a gas disappears and you get a new state of matter called a supercritical fluid. It has properties like a liquid that it can dissolve things, but yet it has properties like a gas where it can kind of fuse through things. They use supercritical carbon dioxide to decaffeinate coffee. And so it has a wide variety of uses. It's a really interesting thing. If you have time to research what it does and what they use it for, it's pretty cool, but otherwise it's kind of beyond the scope of where we're going. But so that's a phase diagram, and that's our states of matter, and we will pick up with gases in the next unit.